Let me ask you something simple. How fast is fast? A cheetah runs at 130 kilometers per hour. A fighter jet pushes 3,500. A bullet from a rifle leaves the barrel at about 1,800 meters per second. Fast, right? The speed of light covers 299,792 kilometers every single second. That's 7.5 laps around the entire Earth in 1 second. And here's the thing nobody tells you in school. That number isn't just impressive. It's a law, a hard limit built into the fabric of the universe itself. And what happens when you push toward it, or try to break it, is one of the most bizarre, beautiful, and deeply unsettling stories in all of science. Welcome back. I'm David. This is Stranger Than Fiction on SciTales. Last episode, we went into the dark. Dark matter, dark energy, the scale of everything, a signal from space we still can't explain, and the slow, inevitable heat death of the universe. If you haven't heard it, go back. Seriously, you'll want the full picture. Today, we're tackling something that Episode 2 teased at the end. The speed of light. Why is it the cosmic speed limit? What would actually happen if you could break it? What does it do to time, space, and reality as you approach it? And here's the one that breaks most people. We're going to talk about what the speed of light means for what you can actually see in the universe, because some things that appear to be out there aren't, and some things we can't see anymore might still technically exist. 5 facts, 21 minutes. By the end of this, you'll never look at a beam of light the same way. Let's go. Segment 1. Why does the speed of light exist as a limit at all? This is actually a question most people never ask. We're told it's the cosmic speed limit. We accept it, and we move on. But the why is far stranger than the fact itself. In 1865, Scottish physicist James Clerk Maxwell wrote down a set of equations describing electricity and magnetism. Buried in those equations was a number, a constant, a speed at which electromagnetic waves propagate. That speed, approximately 300,000 kilometers per second. Maxwell realized these were light waves, and the speed was fixed, not relative to anything, just fixed. That created an enormous problem. In Newtonian physics, the physics everyone accepted at the time, speed is always relative. If you throw a ball forward from a moving train, the ball's total speed is your throwing speed plus the train's speed. Simple, but light doesn't work that way. In 1887, Albert Michelson and Edward Morley did a famous experiment trying to detect the difference in light speed depending on the direction Earth was moving through space. They found none. 0 difference. No matter how you measured it, moving toward the light source or away from it, the speed of light came out the same. This was genuinely shocking. It meant light didn't follow Newton's rules. Einstein, in 1905, looked at all of this and made a radical decision. Instead of trying to explain away the anomaly, he accepted it as a fundamental truth. The speed of light is constant for all observers, regardless of how fast they're moving. And then he asked the question nobody else dared. What are the consequences of that being true? The answer was special relativity, and the consequences were bizarre beyond anything anyone expected. Here's the unknown fact that most people miss. Light speed isn't a limit because nothing can push through it. It's a limit because at the speed of light, time stops completely. Mass becomes infinite. Energy requirements become infinite. The universe isn't enforcing a speed limit like a traffic cop. It's structured in such a way that traveling at light speed would require becoming light. massless, and eternal. For anything with mass, that's not possible. Not as a technical problem, as a mathematical impossibility. The speed of light isn't a wall you can smash through. It's the edge of the map. Segment 2. Let's say you're in a spacecraft, and you start accelerating. You get to 10% of light speed. Things are normal. You feel the acceleration. The stars look slightly bluer ahead of you, slightly redder behind you. A Doppler effect for light called blue shift and red shift. You push to 50% of light speed. Your clock starts ticking measurably slower than clocks back on Earth. This isn't a malfunction. This is time dilation. The same physics running GPS satellites that we covered in Episode 1, scaled up to something dramatic. You push to 90% of light speed. Now something strange happens. To an outside observer, you look flattened, compressed along your direction of travel. This is called length contraction, another prediction of special relativity that has been experimentally confirmed. Objects in motion are physically shorter in the direction they're moving, and your mass, your inertial mass, the resistance the universe has to accelerating you further, is now increasing. The faster you go, the harder it gets to go faster. Not because of friction, because the mathematics of spacetime itself resist it. You push to 99% of light speed. Time for you is now passing at roughly 1/7 of the rate it is on Earth. For every 7 years passing back home, you experience 1 year. Your inertial mass is now roughly 7 times what it was at rest. You push to 99.9999% of light speed. Time for you is running about 700 times slower than on Earth. 700. For every 7 centuries on Earth, you experience 1 year. And here's the fact that genuinely scrambles people. This is not hypothetical. This has been measured. In 1971, physicists Joseph Heffel and Richard Keating flew atomic clocks around the world on commercial airplanes. When the clocks returned, they were measurably different from identical clocks that had stayed on the ground. The flying clocks had ticked slower, exactly as relativity predicted. Particle accelerators do this constantly. Subatomic particles called muons, created in the upper atmosphere when cosmic rays hit, should decay before reaching Earth's surface. Their half-life is too short. But because they're moving near light speed, time dilation extends their life from our perspective. They survive long enough to hit detectors at sea level. We observe time dilation every single day. It's not a theory anymore. It is a measured, quantified feature of reality. Short pause. The universe genuinely slows down time for things that move fast. And as you approach the speed of light, time doesn't just slow. It approaches 0. Segment 3. And this one is personal. Every time you look at something, you are seeing the past. I don't mean that metaphorically. I mean that literally, physically, with exact timestamps. Light travels fast, but it doesn't travel instantly. And in a universe this large, that delay adds up. When you look at the moon, you're seeing it as it was 1.3 seconds ago. That's fine. The moon hasn't changed much in 1.3 seconds. When you look at the sun, and please don't look directly at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. If the sun vanished right now, you wouldn't know for over 8 minutes. When you look at the nearest star, Proxima Centauri, you're seeing it as it was 4.24 years ago. When you look at the Andromeda Galaxy, the nearest major galaxy to us, just barely visible to the naked eye on a clear night, you're seeing it as it was 2.5 million years ago. Homo sapiens didn't exist yet. Stone tools were barely a thing. And when astronomers look at the most distant galaxies we can detect, they're seeing light that left those galaxies over 13 billion years ago, when the universe was less than 1 billion years old. Here's the unknown fact. When we look at the edge of the observable universe, we're not seeing what's there now. We're seeing what was there near the beginning of time. Those distant galaxies we observe? They have moved. Some of them don't exist anymore. They've merged, collapsed, transformed. Some of the stars we see in the night sky have already died. We just haven't received the news yet. The universe you see when you look up is not the universe as it currently is. It's a layered archive, a time machine made of light, showing you different eras of cosmic history simultaneously. Every clear night sky is not a window onto the universe. It's a museum of the universe, displaying exhibits from billions of years across time. Long pause. Let that land. And here's the part that makes this even stranger. Some parts of the universe are now so far away, moving away from us so fast due to the expansion of space, that the light they emit today will never reach us. It's not traveling toward us fast enough. Space itself is expanding faster than the light can cross it. There are regions of the universe we can never see. Not because they're hidden, because the universe is expanding too fast for their light to ever arrive. The universe has a horizon, not a physical wall, a light horizon. Beyond it, everything exists, but we are permanently cut off from it. Segment 4. The one you've been waiting for. Can anything actually travel faster than light? The short answer, based on everything we know, no. Not for anything with mass. But the universe has some loopholes, and they're extraordinary. Loophole 1. Quantum entanglement. When two particles become entangled, a change in the state of one particle is instantly reflected in the other, no matter how far apart they are. Einstein called this spooky action at a distance. He hated it. He spent years trying to disprove it. He was wrong. Quantum entanglement has been experimentally confirmed over distances of thousands of kilometers. The correlation between entangled particles is instantaneous, faster than light. So, problem solved? Faster than light communication achieved? No. And this is the subtlety that drives physicists to distraction. While the correlation is instantaneous, you can't use it to transmit information. The results at each end are random until you compare notes through a normal, light-speed-limited channel. Entanglement is real. Faster-than-light information transfer is still impossible. The universe is exquisitely designed to prevent that particular violation. Loophole 2. The expansion of space itself. Here's a mind-bending fact. When cosmologists say distant galaxies are receding from us faster than light, they're not violating relativity. Nothing is moving faster than light. Space itself is expanding, and the galaxies are carried along with it. Relativity limits the speed of objects through space. It says nothing about the speed at which space itself can expand. And space, apparently, has no speed limit. Loophole 3. The Alcubierre drive. In 1994, Mexican physicist Miguel Alcubierre proposed a theoretical concept now called the Alcubierre warp drive. The idea, instead of pushing a spacecraft faster than light, you contract space in front of it and expand space behind it. The ship sits in a bubble of normal spacetime that moves faster than light. Nothing inside the bubble violates relativity. It's the bubble itself, made of warped spacetime, that moves. The math works. On paper. The catch? The energy required is on the order of the entire mass energy of Jupiter, converted completely. Some models suggest even more. It would require exotic matter with negative energy density, which may or may not exist. And the engineering challenges are, to put it mildly, somewhat beyond current human capability. But no one has proven it's impossible. It is, as far as the physics goes, a valid theoretical framework. The unknown fact that changes everything. In 2021, physicist Eric Lentz published a paper proposing a modified warp bubble that might require far less exotic energy than Alcubierre's original model. The numbers are still enormous by any practical standard, but the field is genuinely active. The question of faster-than-light travel is not closed. Science doesn't say impossible. Science says not yet solved. Fifth and final segment. And this is the one that closes the loop on everything. Here's why faster-than-light travel, if it were possible for information to travel faster than light, wouldn't just be a physics problem. It would be a causality problem. Causality is the principle that causes precede effects. A gun fires, then a bullet travels, then it hits something. Not the other way around. Special relativity ties causality to the speed of light. Because of the way space-time works, the way simultaneity is relative to the observer, if information could travel faster than light, there exist reference frames in which that information arrives before it was sent. Faster-than-light information transfer is, in a precise mathematical sense, the same as time travel into the past. If you could send a signal faster than light, you could, in principle, receive a reply before you sent the original message. Causality breaks down. Effects can precede causes. The universe stops making logical sense. This is why physicists take faster-than-light limits so seriously. It's not just about the speed. It's about preserving a universe in which time flows in one direction and causes produce effects. The speed of light isn't an arbitrary rule someone invented. It is the seam holding the logical structure of the universe together. And here is the fact I want to leave you with. The reason we can think about this, the reason the universe produced beings capable of understanding its own rules, is precisely because those rules are consistent. A universe where causality breaks down is a universe where nothing can build up into complexity. No stars, no chemistry, no life, no brains capable of asking questions. The speed of light isn't just a limit. It's the reason anything coherent exists at all. All right, let's bring it home. 5 facts about the speed of light that should fundamentally change how you see reality. 1. The speed of light isn't just fast. It's a hard structural limit of the universe. For anything with mass, reaching it would require infinite energy. 2. As you approach light speed, time slows down. Not metaphorically, measurably, verifiably, experimentally confirmed. Particle physics proves this every day. 3. Every time you look at a star, you're looking into the past. Some of what you see no longer exists. The night sky is a time machine. 4. There are loopholes. Quantum entanglement, expanding space, theoretical warp bubbles. But none of them allow information to travel faster than light without breaking causality itself. 5. The speed of light isn't just a rule the universe follows. It's the reason the universe is coherent enough to support the existence of things that can ask why. Here's what I want to leave you with. We live in a universe governed by laws so precise and so consistent that they've allowed matter to organize itself into brains that can understand them. That's not nothing. That's the most remarkable thing I know. Next episode, we're going somewhere even stranger. Black holes. What they actually are. What happens if you fall into one. Why time stops at the event horizon. And the information paradox. Stephen Hawking's greatest unsolved problem, which is still unsolved today. If this episode shook your sense of reality in a good way, share it with someone who still thinks science is boring. Let's change that. I'm David. Thank you for listening to SciTales. Stay curious.